Good morning students, I am P. Gomati, Assistant Professor, Department of Mathematics. So in the previous classes we have seen about groups, semi-groups and what is a subgroup and some theorems based on the subgroups. So in this class we are going to see homomorphism of group. So homomorphism is nothing but you have to consider two groups G, star and H, some other notation delta. So if you consider a mapping F from G to H, it is said to be a homomorphism if F star A F of A star B is equal to F of A delta F of B for any A, B belongs to G. Suppose if you consider the same operation as star, you can get F of A star B equal to F of A star F of B. So this is the definition of homomorphism. Next, let me define you the kernel of a homomorphism. So kernel of homomorphism is nothing but if you consider a mapping F from G to G dash, which is a group homomorphism, then the set of all elements of G which are mapped into E dash, that is identity element, is called the kernel of F and it is denoted by KR of F. So X belongs to G such that F of X equal to E dash. That is, we have some set of elements in the group G, let it be A, B, C, D, etc. And in the group G dash, you have many elements, but some elements in the group G can map to the only one element, that is our identity element E dash. So you have to collect all those elements and put it into a group called kernel of F. So kernel of F is nothing but what are all the elements mapped to the identity element E dash is called the kernel of homomorphism or kernel of mapping F. Okay. Next definition is isomorphism. So isomorphism is nothing but again you have to consider two groups G, star and G dash, delta, and these two groups are said to be isomorphic if it should satisfy three conditions. One is F is a homomorphism and second one is F is 1 to 1 and third one is F is onto. In other words, we can call this as bijective homomorphism is also said to be an isomorphism. Next definition is coset. A coset is nothing but if you consider a subgroup H from a main group G and for any element A in G, the left coset of capital H is denoted by A star H and the right coset is denoted by H star A, and A star H is nothing but A star small h where small h belongs to capital H, and similarly H star A is equal to H star A where H belongs to H. So this is our definition of coset. And this is a problem. Let G equal to 1a square a cube where a power 4 equal to 1 be a group and H equal to 1 a square is a subgroup of G under multiplication. You have to find the right coset of H. So the right coset of H in G is given by H star 1 equal to 1 a square. It is nothing but our H. Similarly, H star A equal to A into 1 is A into A square is A cube. Similarly, H star A square is nothing but A square into 1, A square, and A square into A square is A power 4. Here A power 4 value is 1. So A square comma 1, again it is our H. Similarly, H star A cube is nothing but A cube into 1 is A cube into A square is A power 5. So A power 5 can be written as A power 4 into A, and we know A power 4 value is 1, so 1 into A is A, that is A cube comma A, which is again H star A. So we have H and H star A are the two distinct right cosets of H in G. So if we union all these sets, we can get the whole group G. So G is nothing but 1 A square A cube and H is nothing but 1 A square, and order of G is given by 4. Order of G is nothing but number of elements in G. Similarly, order of H equal to 2 and index set which is denoted by Ig of H equal to order of G by order of H, that is 4 divided by 2 is equal to 2. So here we are going to prove a small theorem based on this coset. So any two right or left coset of H in G are either disjoint or identical. If you take any two right coset H star A and H star B, and we have to prove that the intersection H star A intersection H star B is equal to the empty set phi, or simply we can prove H star A equal to H star B. Suppose if you are assuming a contradiction H star A intersection H star B not equal to 5, then there exists an element X belongs to H star A intersection H star B. We always know if X belongs to A and B, then X belongs to A and X belongs to B. So using this concept, we can write this as X belongs to H star A and X belongs to H star B. So X belongs to H star A and X belongs to H star B implies H star X equal to H star B by the previous theorem. So from 1 and 2, H star X equal to H star A equal to H star B. So from this we can say H star A intersection H star B equal to either empty set or it should be equal. Thank you.